We can start? Okay. So, good morning and welcome to the first talk of the last day of this conference in Java. I expected some more people, but maybe they will join. Let's start with my talk with the awesome title, CRaCin Your Java Application. Start so fast I want to cry you. Some short words about me. My name is Dirk Fauth. I'm a research engineer. I'm a long-year Eclipse committer. I'm working for the ETAS GmbH in Stuttgart. We're a 100 subsidiary company of Bosch. And I'm a long-year committer, contributor to Eclipse projects, OSGI, fanboy, if you want to say so. So that's my scope of work. Now, what's the talk about today and what's the motivation of this talk? So we at Bosch and ETAS, we have a lot of Eclipse RCP based applications, but nowadays people tend to say our applications should move to the cloud. So we want to containerize the applications, what should we do and how to proceed there. And when you talk with people about moving a Java application to the cloud, you typically get sentences or statements like, well, the startup of a Java application is too slow for a cloud application. And the size of a container with a Java application is way too big. And my goal was to have a look on how we can deal with these sentences and make clear that Java is a good cloud and container citizen. While the talk about the size of containers, I helped last year at the EclipseCon. So this is not the topic for today. Today I will look at how can we improve the startup of Java applications in a container. Short overview what you have to expect. So I will first start with a general topic, Java in containers, what has happened in that area in the last years. And then I will dive into the CRiU topic and give a short conclusion at the end. So Java in container. What happened in the Java world in the last years with Java in containers? The first thing that's probably for most of us nowadays an obvious thing is that Java introduced container awareness. So when containers came up, the problem with Java was that when the Java VM inspected how many processors it can use and how many RAM it has, it used the information from the host system and not from the container system. So what happened if you were not cautious was that your application failed at some time because it took too many resources. That was changed in Java, so there is this container awareness, and nowadays it's enabled by default, and you have some additional parameters to tweak the behavior of your Java application in a container. The next thing that's probably not directly related to containers, but to Java applications in general and how you deploy them is the introduction of JLink. JLink is a tool by the JVM that helps you to generate your own custom VM. And, well, it helps you to reduce the size of your JRE. So you get this, smaller container sizes. Two important things here. You need JPMS, so you need the Java module system to make it work. And it's only possible to reduce the size of your Java application because if you use all the features, well, the size stays the same. The next thing, and this is probably one of the more interesting things when it comes to startup time reduction, and that's also part of the current Project Laden stuff, is the class data sharing, CDS. So the idea of CDS is that you create a shared memory of the core classes of the library, And you dump these internal class representations into a file, so you don't have to compile and load them on startup every time. And the goal was to reduce the startup time and the memory footprint between multiple Java virtual machines, but it's only about the core classes, so that's the CDS. Now, for your application, that's, well, you don't gain much actually, but there's the application class data sharing, app CDS, that you can, well, you can operate on your application and generate this app class data share for your application classes also. So you store common classes on a shared drive, you reduce the load time of classes, but that improvement of that startup time is only at the time of class loading. And there is no optimization or hotspot detection, so what comes after the class loading stuff. So it's a first step in reducing the startup time of your Java application, but it's not yet the end of the road. So there is much more we can do. And we have AOT, so ahead of time compilation. I have looked at GraalVM, of course, the natural choice when it comes to, in the open source world, on native compiling a Java application. I have OpenJ9 also here on the list. Now, OpenJ9 does not support a native image like it does with the GraalVM, but they support AOT compiling combined with the app CDS. So your app CDS cache can be ahead of time compiled to improve the startup time there. We also have a colleague from the Jamaica VM here, which is a commercial product that also supports native compiling. So as he sits here, I wanted to mention this. There are also commercial products that supports that. Okay, so these are the things that are currently available in Java that helps you to reduce startup time. Now, when I created my presentation for reducing the size of a container, I verified the OpenJ9, I verified the Tambourine and compared these two, and I had issues in the OpenJ9 world. So I had suddenly startup times that took 2 times longer if I used JLink and such things with the OpenJ9. And I told this the IBM guys, and they said, oh, wait, we have some parameters. Have you tried app CDS? Have you tried this and that? And at the end they said, have you tried CRIU? I said, no, what's CRIU? I never heard of it before. And I said, yeah, we in OpenJ9, we are currently working on that CRIU feature. And with this, you have incredible fast startup times. Well, it was at the day of my presentation, so I was not able to evaluate this directly, but I took it as a challenge. And so I started to verify what is CRIU. CRIU means Checkpoint Entry Store in Userspace. It's a Linux project, and it freezes a running container or a running application and checkpoints its state to files on a disk. And you can use these checkpoint files then to restore the application at a later time, and the application or the container will exactly run again from the time it was checkpointed. Okay, and here's the explanation what that basically means. I give a high overview of this topic. If you're more interested in more details in that topic, have a look at the YouTube records of Gerrit Grunwald with the title What the CRaC. He goes much more in detail to explain what happens at the JVM startup. But to make it short, a JVM startup, it consists of several consecutive processes that are repeated. And mostly we have these de-optimizations. So we have the JVM startup, we have the application startup, and then we have this warm-up phase. And the warm-up phase is compiling and optimizing the code, and then it de-optimizes and so on until we are in the state that the JVM is up and ready. Your application is up and ready. And that's the end of the right red line. And well, yeah, the pauses are in between, or the garbage collector pauses, but what we want to do is we want to start our application always from the second red line, because this JVM startup thing happens every time you start your application new. So if I have this in, even on my local machine, if I start the application, stop it, and start it again, the JVM startup phase is always executed again. The CRaC project, or CRIU, aims at, we don't want this because the result is always the same. So how can we make the process that is always the same, how can we skip it? So when I started the evaluation, and it was told to me by the OpenJ9 team that they have the CRIU support, I searched around and came, of course, to the presentations by Gerrit Grunwald, and noticed that there is a project called CRaC, CRaC, which means Coordinated Restore at Checkpoint. Strange name, but that's it. And it's an OpenJDK project, and there's a reference implementation by Azul Zulu. And you can download the Zulu JDK or JRE with CRaC support from their website to directly play around with it. Or you can use the OpenJ9 CRIU support. Now, the OpenJ9 guys didn't know that there's the JDK CRaC project, or the other way around, so they had two different implementations. And it took me a while to understand where are the differences and what's the same. And this table is huge and contains a lot of information. The presentation is online, and you can use it as a reference later on, so sorry for the full-blown slides. But okay, where are the differences? So we have some base images. The Azul Zulu JDK CRaC image is based on Ubuntu JDK. The IBM Semaru images are based on the UBI minimal. So that's for the base images, and well, we only have the JDK. If you want a JRE only image, you have to build it your own. That's not too complicated actually, but there is no default image based only on the JRE. The next thing that struggled me for a while is there an Alpine support? Because the year before I looked on how to create minimal size images. And if I want to have a minimal size image, it's natural to have a look on Alpine and use Musel instead of the glibc. Now, for the Azul Zulu, that's not a problem. OpenJ9 brought out the statement they will never support Alpine and Musel. So this is simply a fact. They use this UBI minimal stuff, and I can, at the end, I have a comparison about the sizes to give you numbers. Yeah, the Azul Zulu has an option to use the J command to generate your checkpoint files manually. That's not in OpenJ9. Well, kind of, because OpenJ9 has introduced CRaC support. I come to this again on a later point of time. The API that is used is on the JDK side, JDK CRaC, which are the packages in the JVM. OpenJ9 has those classes in org Eclipse OpenJ9 CRIU, but they both support now org CRaC, which is an API that's independent of the implementation. The JVM options to enable the CRaC features are also different, of course. We have on the JDK side CRaC checkpoint 2, so this way you enable the checkpoint creation, the CRaC feature, and you tell where to write the checkpoints to. In the OpenJ9, you enable the CRIU support with the JVM parameter, JVM option, but they now support also this CRaC checkpoint 2. As far as I know, it's not yet officially released flag, but it's targeted to be released soon. When you create a container or a Docker image that supports CRaC and you want to run it to create the checkpoints actually, you need additional capabilities, because the default capabilities you have with your Docker containers when you run them avoid that you can do checkpoint operations on a low-level Linux system. On the Azul Zulu side, you only need the cap checkpoint restore, which actually enables checkpoint and restore, and you need the cap sys ptrace. The OpenJ9 additionally wants the cap set pcap because they are changing capabilities on the checkpoint creation additionally. When you are more familiar with the creation of Docker images and run them, there's the SACOM profile, security profile. The Azul Zulu system does not need any change in that area. The OpenJ9 support requires that you disable the default SACOM profile for the generation of the checkpoints. You don't need that later on, it's only for the generation. PID handling was something that was struggling me quite a while. And well, if you create a checkpoint, and especially when you restore from there, you need to ensure that the PID of your Java process is the same from the container where you created the checkpoint and when you restore it, because this is how CRIU works. It needs the same PID. In your runtime, that's typically well, easy that the PID is free. When you are in a container runtime, that gets problematic because, well, you have no real control over what PID does my process have when it starts. So you need to think about this. And that struggled me actually when I created my Alpine image, because on Alpine I use the best practice to use Tiny to have a better control of the processes. But then Tiny is the PID #1. And then all the cool features from the Azul Zulu to have a hand on the PID handling does not work anymore. OpenJ9 does not such have convenient stuff. They simply say run a dummy command 200 times and then you have a high enough PID that never gets conflicted with anything else. And the restore point, well, the CRaC implementation has another JVM option to restore your application from a checkpoint. And the OpenJ9 does not yet have this restore option implemented. At least this was the state the last time I got in contact with the OpenJ9 team. They plan to support this also to make them equally exchangeable. As of now, you need to call CRIU to restore a process. So far from to the differences between the two implementations. Now, how does such a CRiU creation, container creation process look like? Well, first you create your application image. I mean, there's nothing special to it despite the Java opt extra, so the extra options where you configure that I want to create a checkpoint, the option for the policies I'm explaining in a minute, and the third one is just an optimization thing. I don't let the implementation search for the right CRaC implementation. I just tell them, okay, it's all CRaC, JDK CRaC, and the rest is a default container image. I mean, I copy my jar in it, copy some resource files in it, and start the application. With the OpenJ9, here you see how it looks like with the OpenJ9, and the difference is the JVM option. Here I enable the CRIU support, but as I said, they now have also the CRaC support, the org CRaC API support, and there the interesting thing or the difference to the Azul thing is that I need to enable the unprivileged mode by hand. This is the default with the OpenJ9. Unprivileged is a container specific thing, so you don't want your container to be executed in a privileged mode, so it does not have too many writes on your systems. So now that I have defined my image, I need to run the container with the necessary capabilities, and this is what I had already in the table of the comparison. I need to start it with different options. So for the OpenJDK Azul, I just need to use the cap add to add additional capabilities. On the OpenJ9, I need to add an additional capability, and they suggest that you first drop all other capabilities, so you only have the ones that you need, and you need to define the CRaCin profile, or disable the CRaCin profile. Creating the checkpoint, that was kind of, yeah, it struggled me for a while, because the tutorials that I found, and there are actually two, they use the J command on the Azul Zulu side. Sorry, yeah, you can connect. So they started the container, then you connect to the running container, and then you execute the J command to generate the checkpoint files. Now I'm a guy that likes automation. If I want to create my container image, I don't want to create it, log into it, do something, and do something else. I want to run this in a pipeline. So I decided to create this, well, some shell scripts that I put into my initial image that is starting my application as a second process, then sleep for 15 seconds, and then call the J command. Okay, yeah. It's a little bit hacky. On the other side, you could do this programmatically. And this is what I'm actually doing with my applications if I do this now. So yeah, I have some code, some immediate component in my classes or in my application. And at a certain point of time, when I know that this is a good choice to now create a checkpoint, I run this core checkpoint restore code. And on the OpenJ9, that code looks a bit different. But you can find it in the docs. Yeah, there you configure everything around. But the principle is the same. At some certain point of time, you know, okay, my classes are loaded. I'm at a good point of time on my startup, and now please generate the checkpoint. As I said, when the checkpoint is created, the application is frozen, and it persists the state on disk. When you restore, it starts at the end of this. So this code will never reach again on your restored application. Well, despite you implement something wrong. And now that you have created the initial image, you started it. In the started image, the checkpoints were created. Typically, when the checkpoint files are created, your application is shut down and the container is killed, which is the default for containers. If there is no running process, the container is killed. Now we create a new image that is based on our application image and that contains the container the checkpoint files. And additionally, we need to change the command that starts the application, because before we said, please generate the checkpoint, and now we want to restore. So we create a new image via container commit. It takes the old container, creates a new image out of it, and we change the initial command. And for OpenJ9, this is currently the lengthy one here because we call CRIU directly. Handling open resources, that was actually a topic that struggled me last year, and I got in contact with the OSGI specification team, and it turned out it's not an OSGI problem, it's a CRaC problem. It's not even a CRIU problem, it's a CRaC problem. Now, what is the problem? The problem is that you need to handle open resources. So if you have any open file handles or open sockets, CRIU might have problems. Now, CRIU itself says I don't have a problem with open file handlers because I can restore open file handlers. That's how I am designed. But the CRaC guy said, nah, that's too risky for us. If there is an open file handle, we simply throw an exception, open resource exception. We got in contact, or I got in contact with them, and then suddenly I got a response. We have now a way that you can configure which files might be problematic and which files are okay to be still open. And that's this policies YAML file. And for OSGI, the topic is that the bundle files are kept open by the runtime. So you get the meta informations about the bundle at runtime. So these resources are kept open. That's by design. Therefore, with the initial version of CRaC, it didn't work. But with this policies file, I can configure that if there is an open jar file handle and if there is anything open in bundle file, which is the cache, the OSGI cache stuff, then simply please reopen it and don't bother me with those files. The other topic is open sockets. Now, I did an example here that makes sense. So last year, with the size of the containers, I had a go-go shell in a Docker container. Well, that's not a very good example. But a good example is I have a web service, a REST service. So here I took the Jakarta REST whiteboard, created a simple service with a Jakarta REST whiteboard, OSGI Jakarta REST whiteboard, and well, there is a jetty underneath, and the jetty has an open port, and an open port is a problem, even for CRIU. There are example codes, and this is actually an example code from the CRaC guys, that you shut down the connectors when you create the checkpoint. So before you create the checkpoint, you shut down the connectors so the ports are closed, and on restore, you open the ports again. In their initial version, they were shutting down the jetty, and when you started, they started the jetty again, so the startup performance was not there. But with this approach, the startup performance is there. The interesting thing with the CRaC API here is that I can register it statically at the place where it happens. And I have an open pull request in the Jakarta RS whiteboard implementation to add this directly to the Jakarta RS whiteboard implementation, because it's possible with the CRaC implementation because we're registering the resource statically. Why I'm mentioning this? Because OpenJ9 has a different philosophy on this. They say you need to register such hooks at the place where you create the checkpoint. Now that's a really bad thing, considering that I'm using a whiteboard implementation and I have absolutely no handle to the Jetty server to interact with, because that's hidden for me, also by design. So it was a hard time for me to get this somehow working. Luckily, the OpenJ9 guys support the CRaC API now. So these are basically the two blocks compared to the CRaC stuff. Conclusion, although I have more slides than only just a single conclusion slide. Now this graph is from the Docs Azul page itself. So they compared startup times with Spring Boot, Micronaut, Quarkus, XML Transform. And you can see from multiple seconds, they reduced the startup time with a checkpoint to milliseconds. Now I was looking at the Jetty in a Docker container. So I called Docker run and took the timestamp of the Docker run and compared it with the last log entry when the application is ready. And with the OpenJDK, without a checkpoint, it took me 4 seconds until the Jetty was ready and responsive. With a checkpoint, it's about 500 milliseconds. I mean, the connector needs to start up, the container runtime needs to start up, but I think 500 milliseconds for a startup is pretty good. And it's the well, that's the numbers for the example of the Jetty Jakarta REST whiteboard example. And now one of the first questions I got when I said, oh, I want to look at this checkpoint stuff was, what about the costs of the checkpoint? Because it sounds so good, it cannot be for free. And exactly, yeah, and I did only find one sentence in all of these documentations that explained what are the costs without numbers. And well, a checkpoint is files on the disk. And files on the disk have a size. And that size relates to the heap that you're currently writing to the disk. So, yeah, you don't get numbers by those documentations because it strongly depends on your application, how much heap you have when your VM is warmed up. And yeah, the bigger the heap, the bigger the files. And this is now the size comparison. So I looked at Azul Zulu with Ubuntu JDK, and obviously, if you have an image with a JDK, well, you're about 500 megabytes, and then it's 150 megabytes more with the checkpoint files. With a JRE, well, yeah, you save 120 megabytes, and there's the colleague from Canonical, and I listened to his talk about Chisel, so you probably are now even able to create smaller sizes for the Azul Zulu with Ubuntu and JRE. Okay. Okay, yeah, but there are options also with the Ubuntu images now with this Chisel project. Then I have the Alpine JRE, which is currently the smallest thing you get simply out of the box, compared to this OpenJ9 UBI minimal JRE. There you can also see the UBI minimal is still bigger than the Alpine. Yes, you have a question. No, I did not. I just did the simple thing I could do. Okay, so for the audience, for the records, the question was if I did something to compress the heap while I was writing it, and no, I did nothing. Compact the heap. No, I did not, but that would be an option to evaluate if we can save something. Yes? We can add several things to the comparison. I can later come to your booth and we can have a look. Thanks for the pointer. Okay, so from that table you can see that without compacting the heap, we're with the CRaC implementation about 130 to 150 megabytes for the checkpoint files. The OpenJ9 seems to be a bit more efficient, about 90 megabytes for the checkpoint files. So, well, can I give you a strong recommendation to use now CRaC or not? Well, it strongly depends on your use cases. Have you more containers that you start up and run forever? Then the space that you need additionally is probably more costful than the startup time you save. If you spawn multiple of these Docker containers regularly, saving the time in startup is probably more worth it. So that's why I was looking for that comparison. There are already several frameworks out there that support CRaC and CRIU. So Spring has a CRaC bundle. We have Micronaut, Quarkus, and Open Liberty. And Thomas Watson gave the last year several talks and blog posts on using CRIU with Open Liberty. And also thanks to Thomas for your support and everything. So as a wrap up here, comparing to the slides before with the growl, because CRaC and growl are commonly compared against each other. well, you also have a super fast startup, and the only reason for CRaC is to reduce the startup time, which we have proven that it works. You have the peak performance from the first request. You have the runtime optimizations available, which is a difference to a native compiled one, because the native compiled one does not improve over time. The hotspot VM improves over time the code you have. That might be interesting for long-running applications and processes, for short-running applications or things, I don't know, needs to be measured. You have typically a lower CPU and memory usage. And the biggest advantage from all the talks I heard on this topic is that your development environment is the same as your deployment environment. So when you debug anything and you want to reproduce a behavior, it's the same when you develop on your machine and it runs on your container. That's not true for the native compiled one with Graal. So in the talk by Garrett Grunwald, he said they had many customers that said that reported errors in the application, but they were never able to reproduce that issue on their development environment because that was an issue in the Graal compilation. As a negative side, we have a larger memory footprint on the container, like this 150 megabytes for this for the REST application here. You need to think about the opening and closing of resources, if you have any. And one thing that's probably not obvious to everyone, the CRaC thing might leak potentially sensitive data into snapshots. Because if you have a password that's in your heap, you write it also into the snapshot because that's in the heap. So might be a security issue. Yes. Okay, so okay, so the comment was that Graal. So with Graal and the native creation, native image creation, you have this closed world assumption, and there they do all the optimizations upfront. But how did you call it? Fast and loose. So they play fast and loose, so they might lose these optimizations up. Okay. I think it's too late to repeat this. But thanks a lot, James. If you have any questions, please come to James. But I'm also right at the end. Here's a list of links where you can find information that I found interesting while I was researching on the topic. And if it was all too fast and you could not really follow my, my explanations, I have written a blog post on the topic that is explaining everything in detail, so you can have a look there and follow everything. And all the sources are on my GitHub repository, so you can even see this is how I did it and try to reproduce it and do stuff on top of it. And that's it, only 3.5 minutes more than I have. Thanks a lot.